pleasure to introduce Joan Bruna now. And I think for the sake of time, Joan, take it away. Your microphone is off, Joan.
Perfect. Okay, I'm trying to share my screen. Do you see my slides? Okay. Thank you very much, Volkan and Wolfram, for inviting me to this very nice workshop. So yes, so today I'm going to talk about some of the project that I did with my colleague John. It's a project that started during COVID, and you know, it's more like an exploration. And I think that if anything, it can maybe offer you a deep perspective to tie together some of these phenomena that we see about optimization in high dimension. So the story really starts with basically the first stop is realizing that non-convex optimization is really the natural playground for any kind of machine learning system that is, in a sense, nonlinear, that has some kind of nonlinear aspect, right? In the sense that if I think about my learning problem in an intrinsic way, I have some hypotheses. I might want to choose hypotheses that have like good agreement with the data. But as soon as I have a nonlinear parameterization of my hypothesis class, I end up with a function that is non-convex, right? And so we can still, what can we do in non-convex case? Well, we can still say that we can find local minimum quite efficiently. And we know from this series of works by several people, culminated by these papers by Xi Jin, that we can find second-order stationary points in a way that is essentially insensitive to dimension. Right here, there's no dimension cost. So the best case scenario, of course, is if you hit the jackpot, is when you can claim that all the local minima of your problem are also global minima. And this is also called the strict saddle condition. And there's actually some examples where this thing has been shown to be successful. For example, these models when we have deep networks, but without activation function, phase retrieval, some problems in terms of the composition, etc., etc. But of course, that's not what you should expect in a generic case, right? Like generically, you cannot expect to have this strict saddle condition when you train neural networks. And so what can we do? So the other alternative that offers us, that maybe opens up interesting theoretical questions, is to look, instead of looking for optimization of a particular function that is given to us that might be very complicated, look at random optimization landscapes. Try to understand what is the typical case behavior of these learning algorithms. This is an example that I picked from a paper from Samarkand about like a realization of a spin glass energy landscape. And so some examples where we take this framework of studying like random optimization problems come from the probability and physics community, like spin glasses, statistics, high-dimensional statistics, for example, trying to understand tensor PCA, and maybe even more related to this topic of this workshop, these are problems that involve what we call a teacher-student framework. And I borrowed this nice analogy from Florent when he gave a talk about teacher-student. These are the teacher and the student. Okay, so here would be like the two parameters of two neural networks that one tries to follow the other. And so, in a sense, and here what I want to insist is that like optimization and high-dimensional statistics are really intertwined together. They are really tied together. Right? So many of these problems that I described, they do not have optimization in their genes. Right? It's really just you can set up the problem. Say I have some parameter of interest, maybe like some community structure, maybe some hidden direction in a tensor. And I have some observations that depend on this hidden structure, and I want to recover the hidden structure from my observations, right? And you have to think about, we can think about this problem in the limit when P and D go to infinity at a certain rate. So of course, optimization becomes like a central player once we take this variational perspective, right? We try to characterize the solution that we care about as the solution of a certain optimization problem. For example, the maximum likelihood estimator can be written in this variational form. The problem, of course, is that not these optimization problems are not always computationally tractable, right? Sometimes we have very naturally kind of a potential gap that appears between what we can do by writing down these estimators and what we can implement efficiently. And so the kind of the high level questions of today are really understanding in this picture, when are local descent algorithms, in particular gradient descent, competitive in this picture, right? In the sense, when can you legitimately claim that you can solve very well statistical problems with gradient descent. And can we find, like amongst the gradient descent family of algorithms, a template that we can analyze efficiently? Okay, so these are basically the two main high-level questions of today. And so probably I don't need to introduce gradient descent to anyone here, but I just found this very nice animation on the web, and I thought I would just show it. It's very nice, much better than I could do. So gradient descent is really the problem of drawing a ball and letting it fall into the valleys, right? I guess here in Switzerland you have many of these very interesting and nice landscapes like that. And so you can define this algorithm in discrete time by basically taking discrete gradient steps, and you can also implement it in continuous time by the associated ordinary differential equation, which is called the gradient flow. So gradient descent is very nice, but when we combine it with problems in inverse problems where there might be noise, you might very quickly see that there could be potentially a problem, right? In the sense that you could have what's called Hardness in the landscape that could trap these trajectories. These trajectories could be trapped as soon as there's a little bit imperfection along the road. So this, of course, is a very classic phenomena, and we know that there's a very powerful tool to kind of overcome this phenomena, that is noise, right? That we can think about noise as adding regularization. So what does it mean? It means that instead of following these deterministic updates, we are going to kind of perturb our gradients with appropriate form of noise, and this is called like a Langevin diffusion in the technical term. Both, you can define it both in discrete time and continuous time. And we know that through this trick, we can recover something that qualitatively resolve this problem, right? In the sense that if I look at the law of this becomes like a random vector, right? Because these updates are stochastic. So the law of this process concentrates along the global minima of my function, right? As this inverse temperature goes to infinity. But the problem is that this has no, so this is only qualitative, right? In a sense, quantitatively, this has very, very bad behavior in dimension, right? This is something that is called the metastability, right? The fact that the convergence speed to this global minima, as you know, can be exponentially bad. So this is not necessarily something that can result in nice algorithms. So another thing that we can do, and this is really not our idea, right? This is an idea that has been floating around through many, many years, as you can see, is instead like swapping the noise updates with the gradient updates, right? So think about what happens if I put noise before taking the gradient updates. Now this update in expectation is not the gradient as before, right? Because the expectation is somehow, the noise is somehow inside the gradient. So in expectation, I'm basically evaluating the gradient at a point that potentially is different from what I had before. And so how can we understand like this very simple phenomena? So we can understand this phenomena through the notion of a heat semigroup, like a diffusion semigroup. Okay, and this is a very simple, I guess, idea that hopefully everyone will grasp visually. Okay, so consider my original function f, that's the function I want to optimize. And now I'm going to lift the function, right? I'm going to consider a new function that is defined over the same domain plus some kind of time or temperature. And I consider this capital F to be the solution of the heat equation, okay? With initial condition, the function f. So what does this capital F look like? Well, it looks like at the zero temperature, it looks my original function. But as I increase this value s, it applies a diffusion, kind of a smoothing, right? And so we can actually represent this solution as an expectation with respect to a diffusion process. Okay, and this, for technical terms, is a diffusion process that has an associated infinitesimal generator, the Laplacian. Okay. And so what is the heated gradient design in this framework? Is instead of trying to just navigate this landscape that we have here in the top, you can navigate the landscape at different temperatures, right? At different S. So the question is, how does this thing help us, right? Does this thing bring us anything new to the table? And so just to give an example of how this thing looks like, and just to convince you that this thing is something that you can implement efficiently, right? In the case where you have the domain that is just the Euclidean space, this diffusion process is exactly a Brownian motion. And so we can completely represent the solution, like the solution of the heat equation, as an expectation with respect to this, basically with respect to Gaussian variables, where we basically add the noise before evaluating the function. And because of the linearity of the gradient, this also translates to the gradient updates. In other words, if I want to compute the gradient of my lifted function at any given point, I can do it by just drawing a bunch of noisy points. That's the thing that I put here, querying the gradient at all these noisy points, and then taking the average. right? So this thing converges at the statistical rate, doesn't have any kind of explosion here to this object here. Okay, so I can algorithmically implement this algorithm. The other example that we are going to see quite a lot today is when my domain is the unit sphere. Okay, so this is something that will appear later. And so basically the bottom line is that the same story goes through. Technically, you need to replace the Brownian motion by something that is called a spherical Brownian motion. And there's a little bit of something that one needs to correct, because when you could take gradients in the sphere, you need to project into the tangent place. And so when you add noise, the tangent space changes a little bit. So you need to correct for that. But other than that, the bottom line here is that you get basically the same phenomenon. Okay, so you can access these models very well. So let's try to zoom in a little bit into how does this object look like when you try to optimize functions on the sphere. And this is the natural object that appears very naturally is the spherical harmonic decomposition. Okay, so probably here the physicists in the room have already connected the dots, right? I'm talking about the Laplacian operator. I'm talking about function on the sphere. So naturally, the right lens to look at this operator is through the lens of spherical harmonics, which are basically an orthogonal basis of functions on the sphere that behave de facto as if you were doing the Fourier transform. And so I can take my function, my landscape that I want to optimize. I can write it as a sum of functions at different kind of frequency and different regularity. And so every one of these spaces fk is spanned, then it can be spanned by the family of all the polynomials that are harmonic and homogeneous. And so here you can verify. I mean, this is really like the standard harmonic analysis, right? That obviously, because we are in high dimension, the number of high frequencies blows up very quickly with dimension and the frequency. Okay, so the number of frequencies that I have per harmonic grows very quickly. So the point is now that we have this spherical harmonic representation of our function f, in a sense, this representation is preserved as we run the semigroup, right? Because now if we leave the function, the only thing that we need to do is to reweight, to tune down the spherical coefficients, right? And so, this representation is really just because the Laplace-Beltrami operator is diagonal in the basis of spherical harmonics. So in particular, one example that will be useful is to think about like a particular case where my function f is what's called a ridge function. So it's just it's a function on the sphere that it only depends on a projection of the x. So in that case, we know from many very nice works, in particular the nice work by Francis Bach. He did all this calculation for us, and that in that case you can, if you project the function into the spherical harmonic, you get precisely a function that is a polynomial, right? And the polynomial is called the Gegenbauer polynomials that have like all very nice properties, right? So everything here is explicit. All right. So now let me tell you a little bit about what is known, right? What are the results that why do we think that this object is interesting? And I'll try to motivate by a couple of different results that have been obtained not by us, but through by putting these things together in a framework, we started to realize that this object is actually quite interesting. The first problem I want to talk about is tensor PCA. So tensor PCA is the following problem. So you consider like k that is bigger than 2, just to make it non-trivial. So we have an observation that is we observe a tensor of order k that is pure noise plus a rank 1 spike. Okay, so V corresponds to the signal, the thing I care about. And so I can control the strength of signal to noise by this lambda, right, which is the signal to noise ratio. And so questions that people have asked in the few years, like here are a few questions. So how large do you need to put the signal to noise ratio so that I can have any hope to recover the signal V? Then you can ask, okay, how can I do that with efficient algorithms? Or does gradient descent work? So if I take the kind of naive landscape perspective, am I going to work? Are you going to succeed? So the answers have been also like accomplished through a very nice series of papers in the recent years. So the first answer is that you only need to have signal to noise ratio that is at a constant scale, right? A certain function that depends on k, but does not depend on dimension. But then if you wanna find this thing efficiently, you need signal to noise ratio that diverges with dimension. Okay, and so the optimal, like the best algorithms that are known, need a signal to noise ratio that grows like as d to the k minus 2 or 4. But if you look at just gradient descent algorithms or Langevin algorithms, or even like AMP, it apparently does not compete with the best algorithms, right? So there's something about gradient descent that is not as nice as the best algorithm that I have. So natural question for us. Well, I mean, actually, this is a work that is not done by us, but it's an interesting perspective is that there's a series of papers. There's a paper by Anima, Ronge, and Hossein, Mobani, Mojave. There's also the works by Giulio Biroli, who's going to speak, I guess, tomorrow. And then also a work by my colleague, Jean-Christophe Murat, who really just established, like just verified that when I run this heated gradient descent, and I put this like a scale space sufficiently far, I basically recover the best algorithmic cluster, right? So somehow the, like the limitations of gradient descent are kind of overcome, at least in this problem, by just looking at the landscape at the right scale. Another example that might show you that this might be something interesting is what happens in spin glasses. So spin glasses are notoriously hard problems. Like if you really want to test a non-convex optimization algorithm, you should think about what it would happen on a spherical spin glass. It's a very scary problem. It's a very scary object. It's a random polynomial in the unit sphere that has Gaussian coefficients. So these coefficients Ck are drawn by IID Gaussians. And so I can consider what's called a pure spin or mixed spin, right? So a pure spin would be a homogeneous polynomial. So all the terms here have the same degree. And a mixed spin, I have a linear combination of pure spins with different coefficients, right? So these are the coefficients that I described here. And so the pure spins have very, very bad local minimum, right? And we know this work by Benarous and Othinger, and also the work by Eliran. And so interestingly, Eliran a few years ago proved that for appropriate conditions on the mixture coefficients that relate to something quite magic, that is this Parisi formula, actually we can prove that basically the same algorithm that described this heated gradient descent, but now run on the Hessian. So instead of basically smoothing the gradient, I smooth the Hessian, and I take the leading eigenvector. Then actually I basically have the best possible, I succeeded at finding the ground state of this problem. And in fact, it matches the best algorithmic bound, right? So these conditions that I have here are essentially the best we can have. And this is also related to some works by Ahmed, Alaloui, Andrea, and Mark. And so basically these are two serious problems where both of them you get this framework of lifting the problem into the scale space gives you basically the best performance. So then we actually okay, so now let's look at problems that are first problem is let's look at something that has a little bit of this flavor. So this is a problem. This is a model that was introduced by Marc Mondelli, Florent, Urvinke, and Lenka 3 years ago, and then it was also developed by some work with Giulio. And so this is basically a problem that kind of is of the flavor of the tensor PCA. So I have some planted like a rank 1 signal over basically P that is bigger than 2, and I combine it with basically a rank 1 covariance measurement. Okay, so I have two sources of information, and then I try to find the solution that agrees with both sources of information. So if you combine all these together, you end up with this likelihood function that really looks like a combination of a rank, like a rank, like a order K, order P plus order T. And so these authors, they developed this, they came up with this very interesting diagram that basically captures the difficulty of this problem as a function of these two parameters, right? Like the strength of the contribution from the P part and the contribution from the second order part. And so in particular, they identified also a region, right, for when this lambda 2 was sufficiently small, where basically the algorithm, like gradient descent algorithms and large band descent algorithms, would basically be trapped, would be kind of fooled by the higher order part, right? Whereas like algorithms like AMP are able to basically overcome, get rid of the higher order part and just rely on the second order part that has no, dependency on. And so here, what we prove with John is that in fact the heated gradient descent basically recovers the actual threshold from AMP, right? So this phase that is like hard for Langevin, in fact, is not hard for this like enlarged family of gradient descent algorithms. Okay, so here we have, the question of succeeding and not succeeding is in the notion of what's called weak recovery in statistics, right? So you just want to find your global maxima to be correlated with the ground truth. All right. So now let me just now spend a few minutes talking about probably like the topic of this workshop, which is neural networks. So far, I haven't talked too much about neural networks. So let me just try to tell you a little bit how this thing relates. So here now we are going to look at another problem that also has this high dimensional favor that tries to learn neural network in what they call in this teacher-student framework, right? So I have some inputs that are drawn from Gaussian, and then some labels that have been labeled by a teacher neural network. And I'm always my research on neural networks is basically shallow models. So this is like a shallow neural net that has a certain number of hidden units. And the goal is really to estimate this function. And we want to estimate this function with good sample complexity and with limited computational resources. So what is known about this problem? So one of the first positive results was drawn by Zhazong and Peter Bartlett and others that really use like a tensor framework, like a tensor network, tensor methods to recover this function, these weights, assuming on the condition that this first layer weight matrix is well conditioned. Then there was another interesting work that is quite related to what I talk about here, that is by Ronge, Jason Lee, and Teng Yu, where basically they looked at the continuation method, which if you have followed so far, is essentially the sort of thing that we are doing, right? So we are relying on the optimization of another function to say something about the optimization of another function, right? So we are considering auxiliary loss functions to help us navigate the landscape, right? So this is a continuation method, and they show that when the weights in the output weights were non-negative, and also in the condition that this weight matrix was well conditioned, then you could actually do that. What they called it landscape design. It's the same thing. And then there's another like unconditional result, like positive result by Adam Clivens and Shitai Shen, where they use this trick that is called a filter PCA. It's a complicated algorithm. There's no assumptions on the weight matrix, but the price to pay is that the number of hidden units cannot grow up. So it needs to stay at the logarithmic scale with respect to dimension. Okay. So the question really is, where does gradient descent stand, right? We are using gradient descent to train these things all the time. So how does the positive results of gradient descent compare to that? And so here we are going to not answer this question completely. We are going to take a little detour. So we are going to consider what's called a conditional gradient, like the Frank-Wolfe algorithm. And this was connected to the question of learning shallow neural networks by this, again, nice work by Francis. And of course, the Frank-Wolfe algorithms have been very well studied by Martin, who is here at the EPFL. And so let me just remind the setup. So we have a bunch of neurons, J neurons in the hidden layer that are drawn IID from the uniform measure. So we just put the teacher weights, draw them randomly. And we assume the output weights. We don't assume these non-negative weights. We just draw them IID with Rademacher. And then so that's our class of single hidden neural layer. So basically what we are going to do is try to find a function that is in the span of this family of rich functions of neurons. And so the Frank-Wolfe algorithm, basically what it tries to do is that it tries to maintain an estimate, right? So instead of like trying to learn all the neurons at the same time, it tries to learn one neuron at a time, right? And so how can I choose what is the best neuron to add to my family? I'm going to look at the residual, like the current error that I have. I'm going to try to look for the neuron that correlates the best with the residual, right? So just to kind of as a greedy algorithm, right? In that respect. And so because I work in this linear span, I have an underlying convex structure. This algorithm is guaranteed to converge, right? Just because of the way that these weights are, I always stay in the convex hull, etc. So there's nice convergence results from Martin that relate on this problem. The hard part really is how do you solve this first step, right? So like that's the key part, right? And so thanks to the symmetry of the Gaussian distribution, we know that the key, basically the key step of this algorithm is to find maxima or minima of this function, right? And this is really because of the symmetry. You see that these residuals, basically when you correlate them with a neuron, you obtain by standard computation something that looks like a kernel, right? And so you have a kernel that is evaluated at the precise points where you have drawn the neurons. Sorry, this should be a star. Okay, so this is really like a function that we found before, right? It's a sum of rich functions. And so what we show is that if now I try to use this heated gradient descent for this Frank-Wolfe oracle, then we can succeed, right? Under we need to we can make the number of hidden neurons diverge with dimension, but not too fast right now. But the point is that the overall conclusion is that if you plug this oracle into your Frank-Wolfe estimation, you can recover the true function with polynomial time and with polynomial sample complexity. So there's a number of things that we are not happy about this result. First is that this dependency is horrible. It's really not optimal. We believe that we can go to actually D, right? So that's the same kind of result that other papers have. And so the idea why this thing works is that really like the complexity of this problem is already captured in the population loss, right? So first you try to understand that the population landscape is easy to navigate. And then we use like classical concentration results that the empirical landscape is going to concentrate uniformly, right? The gradient and the Hessians of the empirical landscape are sufficiently close to the population landscape, right? So they cannot turn saddle points into bad local minima, right? That's the idea. And this is really a technology that has been used, for example, by this paper by Song, Mei, and Andre. There's another thing, of course, is that the smoothness of the activation function is really what gives us the signal to basically use this heated gradient descent, right? Like the essence is that basically we are replacing the activation function. It's as if instead of the activation function, let's say the value, you were manipulating a certain polynomial, right? And here the relevant polynomial is degree 4, right? This is the first non-trivial polynomial. And so you need the activation function to be sufficiently smooth for this to work. And so this is like related also, as I said, to the problem of landscape design by Ronguet. And also this thing has been carefully understood with a much more careful analysis on sample complexity in the case where J equals 1 by this paper by Gerard Benarrouz and Reza, right? So they're related to what they call this information exponent. So there's all these signals that say, okay, if you have sufficient smoothness in the activation function, then it works. Is this smoothness necessary, right? So what happens if there's no smoothness? So this we basically enter into this lower bound territory, right? And that's going to be almost the end of my talk. And so we can actually start playing the game, opposite game, of saying that actually these assumptions are in fact necessary, right? Here, one of the nice examples is this work by Ohad Shamir, where I consider like a single neuron, right? And the activation function is not going to have the same property as I used so far. So it's not going to correlate very well with a low degree harmonics, right? It's going to be actually a periodic function that has high frequency. So in that case, the landscape that gradient descent is not like full of local minima that are bad. It's actually flat, right? And so unless I'm already at the neighborhood of the right solution, there's no way I'm going to navigate it, right, with a local method, right? And these lower bounds, in fact, extend much beyond gradient descent. So they extend to what's called the framework of statistical queries, which is like a framework to understand computational hardness for statistical problems that basically says that you can learn by interacting with the data through noisy expectations. And so this is actually, there's a bunch of lower bounds that are in this flavor. And so the question that you might ask is, are these hardness results true, like real, or so do they apply to any approximate algorithm, or are they kind of limitations of our like framework? And so this is something that I thought to be related, is that we actually complement this framework by basically using tools from cryptography. Okay, and so here basically we look at the same problem of learning a single neuron. The activation function is also like a high frequency periodic activation, like a cosine function. So we try to play the same game. And so here we have, again, like a problem parameter is really how much noise do you put here, right? So how much noise do you put on the labels? And so just why this problem is interesting in this setup is that we know that this function, even though it's like a bit pathological, you can approximate it very well with a shallow neural net value that has width that is small, like a square root of d. And the fact that this Lipschitz constant diverges is also necessary so that I can make the problem interesting. If that was not the case, if the frequency here was constant, then I could just with the kernel method, I could learn this function, right? This is nice work by Daniel Su. So what we show here is this like statistical to computational landscape, right? So what we show is that depending on this unit to noise ratio, this problem goes different phases, right? That's like the same thing, similar spirit as tensor PCA. So there's one phase where this problem is actually computationally hard, like in the cryptographical sense, right? And there's a phase that is interesting, is that we can actually solve this problem efficiently. But here's the punchline. It's not through statistical queries. It's not through gradient descent. It's not through local methods, right? we have to use like techniques, algorithmic techniques that are really tailored, basically that use like this lattice basis reduction. So with that, that's my last kind of conclusions. I'm hoping that I'll have time to answer a few questions. So what I try to provide is kind of like a perspective to think about some problems in understanding high-dimensional landscapes. I think that random landscapes is interesting. It's actually a rich problem, and you can actually relate, as one of the promises of this workshop, like the geometrical properties of the landscape with statistical properties. And this, for example, is beautifully captured by this overlap gap property that is now being used to establish lots of hardness results. And then things that we don't know yet, that maybe limitations or things that we maybe would like to work on, is that we would like to get rid of this Frank-Wolfe algorithm. So we would like to see if we can actually analyze the actual algorithm directly. Does it help in practice? So right now I show you that this heated gradient descent is useful for proving things. Is it work in practice? I saw a paper by my colleague Anna Choromanska, a recent paper where they actually do experiments with deep networks with that. And I saw from this paper that they seem to get some improvements. That's nice. And then other things that I didn't talk about that I think are also interesting is can time discretization, right? It's something that I put completely under the rug today. Can this thing be used as some kind of like implicit regularization in the sense that it's actually helping you? And this is this, a thought-provoking paper, like papers that are, you look at this edge of stability. This very nice work by Alex Damian. And then, of course, separations between gradient descent and heated gradient descent, I think, are interesting. So with that, I'll thank you very much, and yeah, open for questions.
All right, thank you, Joan. Questions from the audience? Okay, maybe while people think about it, I'll ask a few. So there's a lot to unpack in this presentation, Joan. So we begin by looking at some of these optimization problems, then you introduce some sort of a homotopy approach, which kind of smooths out the landscape that helps with the convergence. Now, then you jumped onto Langevin dynamics, and somehow we ended up converging on the Frank-Wolfe with this heated gradients.
Yes.
Now, so this, I think in the convex cases, homotopy Frank-Wolfe, there are some works in it, at least they should be useful to you. But in the things that you mentioned in the end, from what I understand, you don't handle things like ReLUs, right? You still assume that you have an activation function that is smooth and differentiable, because
I mean, smooth in the sense that it's Lipschitz, right? So I need the activation function to have energy in the low frequency harmonics. So
yes,
value is
because
fine.
ReLU is fine.
Value is fine. Yes, yes.
Then I don't understand, in the, let's say, non-smooth, non-convex minimization, there are some hardness results that says that you can't even certify local optimality. So there needs to be additional assumptions so that you can say something about this, no? Because if you think about it,
yeah, so these are columns. Yeah, so basically these are columns, and maybe just could be good to look at, maybe visualize what I mean here, is that, so these are columns, like if you look at this like toy diagram, where like the statistical answer that I'm looking for my landscape is kind of preserved as I augment the temperature a little bit, right? So these are crazy problems where if I look at the optimization at that level, super smooth, and I look at the global solution, this is useful. It's telling me something statistically useful about the problem, right? So these are, of course, it's not the general situation, right? If, as you were saying, right, if I have a non-smooth, non-convex function, I could completely get washed. I could destroy everything I care about by smoothing just a little bit, right? And this is really this. And so yeah, completely. It's a very good point that nothing I'm seeing here is universal in the class of non-smooth, non-convex optimization problem. Right here, the structure of the problem is such that these problems are kind of robust to this kind of noise, right? And this is an important point.
You mean the smoothing? So because from what I recall, Matus and Maxim had a paper on using Langevin dynamics for non-convex minimization. They were using things like dissociativity property, which is something like nearly strongly convex property. In that case, you can actually give global optimality in the Langevin dynamics, but the dependence on the log Sobolev constant is just exponential. So do you have these kind of things here?
No, so that's why I kind of got away from Langevin, and I said that everything we do is basically it's not relying on the fact that Langevin converges, like it. So it's really leveraging the fact that these smoothing operators, you can estimate them efficiently with Monte Carlo. So there's no course of dimensionality, and then relying on that the problem that I'm trying to solve has sufficient structure, that this structure is preserved at that level, and that's what you need to prove, right? That's where the hard work is from, right? And so maybe just to get maybe another intuitive picture, if you think about like a shallow neural network that has a small number of neurons, let's say that the number of planted neurons is of the order of dimension, right? If they are random, they are going to be kind of almost orthogonal, right? So you think about this and you smooth, you replace the activation function by a polynomial. If the polynomial is like of degree 4, you still have the trace. You can still recover where the locations of these neurons were. That's obviously not the case in general, right? If I have
but then this is similar to learning these multi-index functions, because when you do this, you randomly sample over a sphere and discover the subspace where the neurons live, and then you can get an understanding of the okay.
All right. No, so it's the multi-index functions are in fact something that I think it's what we do is even simpler than that. But it's but you're right. I mean, that's the right intuition.
All right.
It's not a universe. It's not something that can work in general, of course.
All right. So let me not keep you for myself all this time. There are 2 more questions. So maybe we go in order. Wolfram, please go ahead.
Yeah. So thanks a lot. So I was intrigued by these shallow neural networks, as you correctly guessed, in the teacher-student setup. And you had these sort of 2 slides from the end. You had this summary graph where you said there are regions of complexity, polynomial time, hard. Can you just tell me a little bit more? What is the axis? Sort of what is really the parameters? Where are the situations where it's impossible and where it's easy?
Yeah. So that's okay. Thanks. So this is really the x-axis here is the signal to noise, and in this problem it's just measured by how much I'm allowed to perturb the labels, right? So if I have an adversary, and here we just to simplify, think about this noise to be adversarial, right? So you can actually corrupt the noise arbitrarily, like the labels arbitrarily, up until a certain factor. So what we show here is that depending on how much noise you're allowed to put, right? So here in this blue regime, it means that the adversary cannot put almost no noise, right? Like the amount of noise it can put is very tiny. Then what the learner observes is something that has like more like a crisp. You can still see very crisply the periodicity of the function, right? In the case where there's no noise, you would see the output would be a pure cosine function. So the point is that even though if you try to learn this function with gradient descent, you would be totally lost, as I showed you before, right? You would see a landscape that would be completely flat, right? Unless you name the right direction, you would be totally lost. We can use the fact that we can use the underlying discrete structure of the problem to actually learn efficiently. And this is something that is the algorithm that is used here is something that is based on what's called the Lenstra-Lovász algorithm. It's an LLL algorithm. Okay, so this is really not something that is in this picture of, you should not imagine a landscape, right? It's more like you have an algorithm that kind of uses a lot the structure of the problem. The interesting part on this diagram is the yellow part, where the yellow part, what we are saying is that if you, so we know that in the yellow part, like if you do MLE, like a statistician that has infinite resources would be able to learn the function, right? Just try to, optimize the likelihood of this thing with respect to the parameters. So that's possible. But if you had an algorithm that was able to do that, then you would be breaking modern cryptography, right? You would be essentially, you could use your algorithm to basically solve a problem that everyone believes that is hard, right? And it's in a sense, to the extent that is the basis of modern post-quantum cryptography. And this is what we call this cryptographic hardness, right? It's relying, yeah.
All right, maybe for the interest of time, we have 1 minute. Zhichin, if your question is quick, please go ahead. Otherwise,
okay. Okay. Hi, John. My question is, can you give some intuition of the noise in a heated gradient descent is purely independent of this loss landscape, how it can benefit in the training?
Yeah, so that's a good question. So I talked about noise just because I wanted to have a way to motivate this thing, but you can see that there's no noise in the analysis, right? So what we are looking at is at the mean effect, at the expected effect, right? So if you look at the Langevin dynamics, of course, the expected move has no effect of the noise, right? There's no, you are basically, the effect is basically felt at the quantity level. But here for this algorithm, you can actually think about, so you can forget about the noise and just say that instead of looking at the function at the landscape X, as Volkan was saying, right? You basically think about the continuation method, right? Like an homotopy. So you smooth the function. How do you implement, right? If you wanted to run this algorithm in a computer, how do you do it? Well, you rely on this like representation in terms of an SD, right? So you know that the function that you're looking for, you can write it as an expectation of some diffusion process. And this gives you like the algorithmic recipe to do that, right? So the analysis that we do is at the level where you assume that there's no sampling error. In some of the works that I cited, there's actually analysis that look at the variance of the estimator, and it basically you're going to make a price. It's going to cost you in terms of iteration complexity. It's going to, you know, the iterations are going to cost you more, but it's always going to be polynomial scale, right? There's no computational hardness that is lurking in that step.
Okay, thanks.
All right. Let's all thank Joan again. Emmanuel, you have a question, but I suggest you maybe email Joan about this. It's an interesting question, but unfortunately we're out of time. So thank you, Joan.